This is lesson 11.1. I will be walking through a chi-square goodness of fit test. From the previous video, we collected a sample of 60 plain M&Ms from a great big bag. So our population is actually the great big party size bag. That's the population. Our sample is 60 randomly picked plain M&Ms, and what we want to do is to see if our sample distribution, what we observed, is similar or about the same as what was expected or what's claimed, or if it's not. So we will do very similar calculations. If it's way far off, if what we see is way far off from the claim, well, then we will reject the claim, reject the null hypothesis, and conclude that there's a difference. But if our sample is really not that far away from what's claimed, well, then we would have no reason to reject the claim. So here we go. We have the given information from the internet of the color distribution from the Cleveland plant, which is where my M&Ms came from. And let me fill in the table. From the previous video, we found 13 blue, 7 orange, 15 green, 11 yellow, 8 red, and 6 brown. That's a total of 60. To find the expected counts, we have to do a little calculating. The expected blues is 20.7% out of 60. So 20.7% out of 60 turns out to be 12.42. And I believe that's the exact answer. We did not round at all. You should always write your expected counts in decimal form because usually they are. Usually they're not going to come out exactly the same, especially with crazy percentages like this. So if we go on down the line and take 20.5% out of 60, we get 12.3. The green percent is 19.8 out of 60. That's 11.88. And we leave all the decimals in there, at least for our table. For yellow, 13.5% of 60 would be 8.1. For red, 13.1% of 60 is 7.86. And for brown, the expected count is 7.44. And if you wanted to check those, you would want to make sure they add up to 60, which they do. I checked that already. Now we want to figure out, all right, how do we measure offness? I mean, clearly there's just the difference, like the blue is 0.58 off from what we expected. The orange is 5.3 lower than we expected. The green is, 3.12 higher than we expected, etc. So we can do just the common differences, but of course there's a deeper mathematical theory behind this. We could just add up all the differences, but of course, if you think about that, if you add up all the differences, you get 0. So that would not be very helpful. So just like standard deviation calculation involves squaring, we are going to, in fact, I'll just write the formula. This is on your formula sheet. But the chi-square test statistic is going to be the sum of all 6 of these blanks that we're going to come up with, those right there. We're going to add up all of those. But what we're going to calculate in each of those is the observed minus the expected, which that's pretty common sense. That's really just the difference between what we got and what we thought we'd get. But to keep it positive, we're going to square that difference, and then we're going to divide by the expected. So it's kind of like, going off of the expected, how far off are we? So it's like the squared difference that we got out of what we would have expected to get, and there's kind of a mathematical reason why that is a good thing to do. And we do that for each of the 6 colors, and then we add them all up, and that's going to be our chi-square test statistic. And of course, you can imagine if every expected count was exactly the same as every observed count, well, then the numerator would be 0 for all 6 of those, and you'd have no chi-squared value, or it would be 0, I guess. The 0 would be the chi-squared value. So any kind of a difference at all is going to give you a positive chi-squared value. So maybe you can imagine that if you would look at the chi-square distribution, you can't get any lower than 0. And over time, what turns out to be true is the chi-square distribution is not symmetric. The chi-square distribution is actually skewed to the right. But anyway, let's go back and just do one of these calculations. For the blue, for instance, the observed is 13. The expected is 12.42. If we squared that and divided by 12.42, that would give us the chi-square component or the contribution for blue. And then for orange, it would be observed, which is 7, minus expected, which is 12.3 squared, over the expected 12.3. And you would do that all the way through, and when you add them all up, then you'll get the chi-square value for the entire problem, which I've already done using a computer calculator, and we get 4.45. But I just wanted to show you a couple of these, and you know, probably you'll never have to show all of these. What you might do for work is just show one or two of those calculated by hand and then just say plus dot dot dot, because the calculator is going to give you the 4.45. It'll give you like the final total, and that's all we're really interested in. But we're kind of working ahead just a little bit. Let's go back and now start from the top, so to speak, with a chi-square test that's called goodness of fit. We're going to start out with a null hypothesis and an alternative hypothesis, just like we would with any other test. It is going to be a little different because our test now is for an entire distribution of 6 colors. We are testing a distribution. So our null hypothesis is going to be about a distribution. And what we're hypothesizing is that the distribution of M&M colors in this party bag, I'm going to erase this because that was just a little scribble, in this party bag is, and this again is something new with the curriculum that is in vogue now, and this is what the rubrics will be expecting you to do. You have to list the percentage of all the colors. This is a little different. We used to not have to do this. So the distribution of M&M colors in this party bag is, and we just basically have to copy that down, 20.7% blue, and we can abbreviate 20.5% orange, 19.8% green, 13.5% yellow, 13.1% red, and 12.4% brown. You do have to list them all out. That's what it says in the new curriculum guide, and so we are going to do that even though it takes a little time. The good news is, though, the alternative hypothesis, think about if the distribution is not these 6 numbers. If you think about it mathematically, there can't just be one of them that's off, because if one of them is too high, well, then there's got to be another one that's too low. So we want to say something like at least, the alternative would be at least 2% are not as expected. I guess you could say at least 1, but the reality is there's got to be at least 2. If they're not all like they're supposed to be, then there's got to be at least 2 that are not as expected. And we've already defined everything we need to define. That null hypothesis takes care of any sort of extra description that we need. So the second step would be the conditions. And again, what I like about the way the new curriculum describes conditions, and I think I mentioned this in some of the classes, really there's only 2 categories of conditions that we have to check with anything. One is independence, and one is sample size big enough. So if I kind of classify these as 2, there's really 2 general categories of conditions. Independence is one of them. And for independence, the first thing you check with independence is that the sample was random. So that was true. I did collect these randomly as I could. The sample was indeed random. And then the other thing that helps guarantee independence is that 60 is less than 10% of all M&Ms in the bag, in the party bag. Those 2 conditions are what help guarantee independence from one M&M to the next M&M to the next M&M. So if you think about conditions as 2 broad categories, that may help us nail the conditions we need. The second thing is that our sample size is big enough. And we've had a couple different rules about that. If it's means, we like n to be at least 30. If it's proportions, we like n times p and n times 1 minus p to be at least 10. Here, we want all expected counts to be at least 5. And they are. All expected counts, and we've got them listed up there. They're right up there. All expected counts are greater than or equal to 5. And we've got that right here. We've shown the work. And so we don't need to write those again because they're up there. We would just say all expected counts are greater than or equal to 5. And those are the 3 conditions for a chi-square goodness of fit test. So we will proceed, because they're all met, we'll proceed with a chi-square goodness of fit test. Goodness of fit test. Now in the future, you are free to say GoF. GoF is a commonly understood and allowable abbreviation. So in the next ones, you can just say proceed with chi-square GoF test. That's what it's called on your calculator. Speaking of your calculator, now is the time to grab your calculator. And if you go to Stat and over to Tests and go way down toward the bottom, there should be a chi-square goodness of fit test. At least if you have a newer operating system. If you have an older calculator like I do at home, an 83, you will not have this. So you'll have to do it all with lists. But the first thing you want to do is, I guess I could write it up here. The first thing we want to do is type in all the observed counts into list 1 and all the expected counts into list 2. So you can pause this if you need to. Put the 6 observed counts in list 1 and put the 6 expected counts in list 2 with all the decimal points that we need. That'll be more accurate. And once you do that, then when you go to Stat, Tests, Goodness of Fit, you're going to conduct a chi-squared goodness of fit test. You're going to use list 1, you're going to use list 2, and then you've got to know degrees of freedom. So here's a new definition. Degrees of freedom is still n minus 1, but n is not the sample size. It's not 50, it's not going to be 59. N has been redefined as the number of categories. This is a big difference from n minus 1 when you're doing means. So it's still n minus 1, but it's the number of categories, number of colors in this case. So we have 6 colors minus 1. Degrees of freedom is going to be 5 for this chi-square goodness of fit test. So if you do that all electronically, you will find that the chi-squared test statistic is 4.45. And then if I can draw that, that distribution again, a chi-squared distribution is skewed right. 0 is the lowest that it could be, and it never is in real life. And what we found out is that 4.45 is out here somewhere. And in this case, it turns out to be like somewhere in there. The p-value will then be the tail to the right. P-values for chi-square tests are always tails to the right, areas to the right. And you'll see that the p-value on this problem is pretty high, as it is in my picture. The p-value is 0.49, really, really high p-value. It's almost half of the distribution is shaded in. And you know what to do with a high p-value, because the p-value is greater than an alpha level. We'll pick 0.05. We fail to reject the null. That's the same decision we would make with any test we've ever done. So there is no convincing evidence. There's no convincing evidence that the distribution of colors, remember this is a test about distribution, there's no convincing evidence that the distribution of colors in this party bag are not as the company claims. Something like that. Now let's read that again to make sure it's right. This is kind of a double negative. There's no convincing evidence that the distribution is not as the company claims. No evidence that it's not as they claim. Remember, this is not proving that the distribution is as the company claims, but apparently it's close enough that we cannot reject it. That's essentially where we landed. So that, ladies and gentlemen, is a chi-square goodness of fit test, top to bottom. That is what you would do for any similar problem. Like, for instance, the next one is about Mendel's P's. If you've had any sort of genetics units in your science classes, you've heard about Mendel. And he had this calculation that he believed was true using genetics with dominant and recessive genes and that sort of thing. And he did a famous experiment with peas. And so here's some counts from 4 different types of peas. And because he's got these fractions or these percentages, we can do just like we did with the M&Ms. You can calculate the expected counts. Of course, you've got to get the total first. Calculate the expected counts, calculate the chi-squared, and go through the whole test from top to bottom. So your practice is simply going to be doing different parts of a chi-square test from different situations. It's a very unique test for a very unique type of data. It's only for distributions, and it's only for counts that are whole numbers. Your data will be whole numbers. So there you go, and I will see you soon in class.